Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss a very important topic which is called as gyromagnetic ratio. But before starting the gyromagnetic ratio, let us first of all discuss that what is magnetic moment. You should have heard about the fact that you could not separate the two poles of a bar magnet, which means that if you subdivide a bar magnet into two parts, then there would be a new south and new pole created in each smaller part. So you could not separate south and north. This is a very important property which I would be discussing with elaboration in later part of the playlist. But now let us first of all see that what is magnetic moment. So we know a fact that just like in bar magnet, we know that in bar magnet, if we draw the field lines of a bar magnet, then bar magnet field lines are from north to south outside the magnet, and inside the magnet they are from south to north, like that. Okay, so bar magnet is also a dipole because there are both the poles in it, and obviously any magnetic source which is creating some magnetic field will be a dipole because magnetic poles cannot be separated. So we are concerned to find out the magnetic dipole moment of a current carrying ring. Now, why we are considering a current carrying ring as a magnetic dipole? Due to the fact that we know that a current carrying ring creates a magnetic field at the center and in the space near the center and outside the ring. And we know that magnetic field could exist only when there are both the poles. So obviously there would be both poles in the ring because it is creating a magnetic field. And if the current is flowing in clockwise sense, then we know that the magnetic field will be going inside the plane, which is cross. Which means that if we again consider a bar magnet, and if we see that inside the bar magnet field is from south to north, so if we are observing the bar magnet from this point, then field is going inside, okay, and therefore we are observing a south pole. And if we are observing the bar magnet from the other end, from this end, then field is coming outside and therefore we are observing a north pole. Therefore when the field is coming outside in the ring, then we are observing a north pole, and when the field is going inside the ring, then we are observing a south pole. This also means that if we are observing this ring from above, then we are observing a south pole, and when we are observing this ring from below, then we are observing a north pole, which means that both poles coexist in this ring, and therefore this ring can be regarded as a magnetic dipole. So the magnetic dipole of this ring M is proportional to the current flowing in the ring, and is proportional to the number of turns in the ring and the area of the ring. And the proportionality sign is obviously 1, so it is NIA, where N is the number of turns. I am writing it down here. So N is number of turns and I is current flowing in the ring, and A is the area of the ring. And obviously we know that in this case the magnetic field is going inside, and in this case the magnetic field is coming outside, and the direction of magnetic dipole moment M will be this is direction, so its direction will be from south pole to north pole, south to north. And the unit of M is NIA, where N is unitless quantity, I is current, so it is ampere, and A is the area, which is meter square. So the unit of magnetic dipole moment is ampere meter square, and its direction is from south to north. So we can say that in this case, when the current is in clockwise sense, this is CW current and this is ACW current, then we can say that the magnetic dipole moment will be inside the plane, going inside the plane. And when the current is in anti-clockwise sense, then the magnetic dipole moment will be coming outside this plane. Now let us discuss important concept of gyromagnetic ratio. Now first of all, let us see that there is a charge which is rotating about this point in a circle of radius r with angular velocity of omega. And if we find out the current analogy, or if we consider this charge as a current carrying loop, so if we find out that current, then that current would be q omega by 2 pi. And the magnetic moment created by this current carrying loop will be NIA. N is obviously 1, I is q omega by 2 pi, and area is pi r square. So cancelling this pi with pi, M will be equal to q omega r square by 2. Okay, so this is the magnetic moment, and if we write down the angular momentum of this rotating charge, then it would be I omega, and I is m r square into omega. So if we find out the ratio of m and l, now this ratio is the ratio of magnetic moment to the angular momentum of this charge, and this is called as gamma. Gamma is gyromagnetic ratio. This is called as gyromagnetic ratio, and this ratio is equal to, you can divide these two terms, then you can see that this ratio will be equal to q by 2m. So this is a universal law that gyromagnetic ratio for any charged object that is rotating, and the charge distribution and mass distribution are same and symmetrically distributed, and for that rotating object, the ratio of magnetic moment and angular momentum, which is also called as gyromagnetic ratio, will be constant and will be q by 2m, where q is the total charge of that object and m is the mass of that object. So let us again check this fact for a rotating ring. So we have already discussed that in a rotating ring, I will be equal to q omega by 2 pi, and therefore m will be equal to NIA. So it would be q omega by 2 pi, and area is pi r square. So m will be equal to q omega r square by 2. Now again, if we write down the angular momentum of the ring about the center, then it would be I com omega, and L will be equal to I com, which is m r square omega, and m by L will be equal to, again you can see that it would be q by 2m. So the gyromagnetic ratio will be constant for all symmetrically charged objects. Now when I say symmetrically charged, I mean to say that the way of distribution of mass and the way of distribution of charge should be same. Okay, yeah. So now if we if we have to find out the magnetic moment of this rotating disk, the first method which will come in our mind will be the integration by considering an element in form of a ring. But to skip that long method, which is the method of integration, we can use the fact that the gyromagnetic ratio of this disk will be q by 2m, and it would be equal to m by L. So m of this disk, rotating disk, will be equal to q by 2m into L, and magnetic moment created by this disk will be q by 2m, and L is the angular momentum, and angular momentum is I omega, and I of this disk is m r square by 2, and omega is the angular velocity, so cancelling m with m. So m of this disk will be equal to q r square omega by 4. This will be the magnetic moment of this disk, and we can find out it by gyromagnetic ratio. Now also in the case of a rotating rod, we can see that if we have to find out m, then we know that gamma is equal to m by L, and m will be equal to gamma L. So m will be equal to gamma into L is I omega. Now we know that about this axis the moment of inertia of the rod is m L square by 3, and omega is the angular velocity, and gamma is equal to q by 2m. So m will be equal to q by 2m into m L square by 3 omega. Cancelling m with m will be equal to q omega L square by 6. This is the magnetic moment of this rotating rod. Now let us find out the magnetic moment due to a hollow sphere, charged hollow sphere, by using gyromagnetic ratio. So gyromagnetic ratio gamma is again m by L, and m is equal to gamma L, and m will be equal to gamma, which is q by 2m, and L is the total angular momentum. So the angular momentum of this sphere about the COM axis will be equal to 2 by 3 m r square into omega. Cancelling m with m, 2 with 2. So m will be equal to q r square omega by 3. And if sigma is given, we can we can replace q by sigma into 4 pi r square. Okay, so we would be getting that exact value. Now in the case of solid sphere, we know that m by L will be equal to q by 2m, and m will be equal to q by 2m into L. L is 2 by 5 m r square omega, and therefore m will be equal to q r square omega by 5. This will be the magnetic moment created by a solid, uniformly charged, non-conducting, rotating sphere. So the gyromagnetic ratio is actually the ratio of magnetic moment and angular momentum of any charged body that is rotating about some axis, and this ratio will always remains constant q by 2m, provided the fact that mass and charge distribution are either uniform, or if they are variable, then their distribution equations should be exactly same. Then in that cases q by 2m will be constant for all type of charge distributions and mass distributions. So this is called as gyromagnetic ratio. Thank you.